starting with our derivative. Set it equal to 0. You can factor out a 15x squared, leaving us with x squared minus 1, which factors further. X plus 1, x minus 1. Nicer numbers. Negative 1, 0, 1. And because this one factored nice, when I'm checking values, I'm going to be plugging them into this factored version here. So if I try a negative number, first of all, this part is always going to be positive because it's 15x squared. So checking a negative is only really checking these two. A big negative number will make both of those negative, meaning that our first section is positive going up. Negative 0.5 will make this section positive, this one negative. This one, 0.5, will have one section negative, and this section positive, negative. Is this one still negative? Negative, yep. Cool. And then finally, wait a second. Something's not right here. It's right so far? I don't like how, oh, I'm looking at this one. I'm thinking my final graph should be an x to the 4 graph, and it wasn't looking right, but it is an x to the 5 graph, so it's okay that it's ending in two different directions. So what I did there is a check, and this is something that you're doing when you're graphing. I knew, well, my check was actually wrong because I was thinking of my y prime graph, which is an x to the 4 graph, which should end either both up or both down, depending on if it's positive or negative. So I was doing my graph here, and it was feeling like it's going in opposite directions on the end. That doesn't match with my x to the 4 graph as I know it. So I was like, a little hesitation, wanting to check my work. Sometimes it's nice not to spend 15 minutes doing something wrong, only to realize you're wrong at the end. Okay? Of course, here I was checking the wrong thing to realize I was wrong, but at least I was checking. Because if I would scroll back up, yes, the original equation is an x to the 5, so it does make sense that it's going up to begin with and then ending going up. So there we have, so this is our first derivative test. We have a maximum, a minimum, and an inflection, stationary inflection point. So if we list them, negative 1 comma something, 0 comma something, and 1 comma something, we're going to know that this one is a local max, this one a stationary point of inflection, and finally this one is a local min. Do you have those values ready? Negative 1 comma 1.24? 2? Okay. It's like, all right, that seems like 0, 0, and 1 comma negative 2. Awesome. Now we'll scroll back up to our second derivative right beside it. Oops. So we get 60x cubed minus 30x. Set it equal to 0. We can take out a 30x, leaving us with 2x squared minus 1. And if I split it here, x could equal 0. And this one, x will equal plus or minus square root of 1/2, which will be plus or minus 1 over root 2. Putting those on our graph here. We're going to check our values. First of all, big negative numbers. This will be positive, this will be negative. Concave down. Between 0 and negative 1 root 2. Okay, what's going to happen Between those points, this is going to be negative, and this is going to be negative, making it positive. Between 0 and 1 root 2, this is going to be negative, and this is going to be positive, making it all negative. And finally, a large positive number will be positive again. So now we've got our, well, let's list them here too. We haven't written our points out. Negative 1 over root 2 comma something, 0 comma 0, which we already knew, and 1 over root 2 comma something. What values did you get here? 1.24 here for both of them, and negative 1.24. Verification, yes. Okay. As far as graphing this, negative 1 over root 2 would be decimal 707. Okay. One of the useless numbers that I have memorized. Yeah, it's from your pie plate. Sine of 45 degrees is 0.707, which is also 1 over root 2. And all of these are inflection points. So we found our y-intercept, so we wouldn't have to do that. Going back to our original equation, could we find more x-intercepts? Well, if we set it equal to 0, we could factor out an x cubed to begin with, leaving us with 3x squared minus 5. Setting this equal to 0, you will get plus or minus the square root of 5 over 3 as 2 more x-intercepts. So yes, you could find some more x-intercepts without your calculator. So to set up our points here, I'm going to look at the overall thing. By the way, square root of 5 divided by square root of 3 as a decimal is something. That is correct. Oh, it's actually a little bit more than something. We define something as 1. It's just a little bit more than something. Plus or minus 1.29. So all of our values, both in the x direction and the y direction for what we have, don't go past 2. So we can sort of set our graph, our scale this way. We're going to have negative 1 comma 2 as one local max, 0, 0 as an inflection point, stationary point of inflection, and 1, negative 2 as a minimum. We know that we have decimal 707 comma negative 1.24. Decimal 707 comma negative 1.24 and negative 707 and 1.24 as our inflection points. And then we have our final 2 intercepts were 1.29 and negative 1.29. Now, again, when I go to graph this, I'm going to use my inflection points as my starting point for my overall graph. So I know that this first part is going to be concave down. This part is going to be concave up. This part concave down. This part concave up. Fancy.